The test stand was shaking. Not vibrating. Shaking, like an earthquake was happening inside the concrete foundation, and Paul Schmidt's hand was 6 centimeters from the ignition button that would either prove his 3 years of calculations were correct or blow the entire workshop into fragments small enough to fit through a sieve. The pulse jet engine was mounted to the stand with 4 heavy-duty bolts that looked inadequate now that Schmidt was actually about to fire it, and safety chains were looped around the engine housing as backup, which would help exactly not at all if the combustion chamber ruptured and turned 30 kilograms of sheet metal into shrapnel, moving at velocities that would punch through brick walls. His assistant was behind the blast shield. Smart decision. Schmidt was standing in the open because someone needed to observe the ignition sequence, needed to verify that the shutters opened correctly and the fuel injected at the right pressure, and the combustion cycle established itself properly instead of just exploding once and destroying everything. These observations required being close enough to see details, which meant being close enough to die if something went catastrophically wrong. And Schmidt accepted this because the engine was his design, and his calculations, and his responsibility to prove it worked or admit it failed. The fuel tank held enough gasoline for 47 minutes of operation at maximum thrust. 47 minutes was longer than anyone needed to prove a pulse jet could sustain continuous combustion. But Schmidt wanted margin because tests always consumed more fuel than calculations predicted, and running out of fuel halfway through a demonstration would raise questions about whether the engine had failed or just run dry. Better to overfill. Better to have certainty. Better to run the engine until it proved beyond doubt that self-sustaining combustion cycles were real and not theoretical fantasies that worked on paper but collapsed when exposed to actual physics. The calculations showed the engine would produce 200 kilograms of thrust. 200 kilograms sounded small compared to 1,000-horsepower radial engines that powered conventional bombers, but those radial engines weighed over 1,000 kilograms and cost 8,000 Reichsmarks to manufacture and required precision machining and rare materials and skilled labor. Schmidt's pulse jet weighed 30 kilograms, cost maybe 200 Reichsmarks to build, and could be assembled in days by semi-skilled workers using basic metalworking tools. The thrust-to-weight ratio was 7-to-1, better than any piston engine in production, better than the early turbojet designs that Frank Whittle and Hans von Ohain were developing in Britain and Germany. But none of those calculations mattered if the engine didn't fire. Schmidt pressed the ignition button. The spark plug clicked. Fuel injected into the combustion chamber. Air rushed through the spring-loaded shutters at the front of the engine. The mixture had 3 seconds to reach the right fuel-air ratio before the spark plug tried to ignite it. And if the ratio was wrong, too rich or too lean, the engine would either flood or fail to light, and he would need to purge the chamber and start over, and starting over meant admitting that his calculations about fuel injection timing were wrong, even though he had checked them repeatedly and verified them independently and tested the injector mechanism 50 times in isolation. The spark plug fired. The fuel-air mixture ignited. The combustion chamber exploded. Not catastrophically, not destructively, but explosively in the way that combustion engines were supposed to explode, converting chemical energy into expanding gases that created pressure that needed somewhere to go. The pressure slammed the shutters closed, preventing backflow, forcing the exhaust gases out the rear of the engine at velocities that created thrust, creating forward force, creating propulsion from nothing but physics and fuel and simple mechanics. But the elegant part wasn't the first explosion. The elegant part was what happened next. The exhaust gases rushing out the rear created a vacuum behind them, negative pressure in the combustion chamber, and that vacuum pulled the shutters open against their spring tension. Fresh air rushed in to fill the vacuum. Fresh fuel injected automatically through the system Schmidt had designed. The mixture ignited from residual heat in the chamber. No spark plug needed now. The chamber was hot enough that fuel auto-ignited on contact. Second explosion. Shutters slammed closed. Exhaust forced out. Vacuum created. Shutters opened. Third explosion. Fourth. Fifth. The cycle was self-sustaining. 50 explosions per second, each explosion taking 20 milliseconds from ignition to exhaust to vacuum to refill. No external power needed once the cycle started. No moving parts except the shutters that opened and closed through mechanical automation driven by pressure differentials. Just a tube that turned gasoline into thrust through elegant application of physics that most engineers never considered because they were trained to think in terms of continuous combustion and turbine stages and compression ratios. The sound was overwhelming. Not loud. Overwhelming. A buzzing roar that shook the building's walls and vibrated Schmidt's teeth and made his assistant cover his ears even though he was behind the blast shield and supposedly protected from the noise. The sound was physical, felt in the chest and bones and skull, felt as vibration rather than heard as audio. 50 explosions per second created a buzzing tone that oscillated at frequencies designed by accident rather than intention, creating harmonics that were unpleasant and mechanical and wrong-sounding in ways that Schmidt knew would make military officers dismiss the engine as crude the moment they heard it. But crude didn't mean ineffective. The test stand was pulling against its bolts with forces that concrete foundations were barely containing. The thrust gauge showed 195 kilograms, close enough to the calculated 200 that Schmidt knew his mathematics were correct, close enough that the 5-kilogram deficit was probably measurement error or air pressure variations rather than fundamental flaws in the design. The engine was working. Self-sustaining combustion was happening. The pulse jet was real and functional, and proving that 3 years of research had produced something revolutionary that would either change warfare or be dismissed as a noisy toy depending on whether anyone with authority was willing to listen. 30 seconds had passed. Schmidt checked the fuel flow meter. Consumption was exactly what calculations predicted. The shutters were opening and closing with perfect timing. The combustion chamber temperature was high but stable, not climbing toward dangerous levels that would indicate thermal runaway. Every parameter was within acceptable ranges. Every system was functioning as designed. The engine that shouldn't work according to conventional aerospace engineering wisdom was working perfectly, demonstrating that conventional wisdom had blind spots, and those blind spots could be exploited by engineers who understood physics deeply enough to recognize possibilities that textbooks didn't mention. 5 minutes. The noise had become background, still overwhelming but now familiar enough that Schmidt could think through it, could focus on measurements and observations instead of just enduring the sonic assault. His assistant had stopped covering his ears and was taking notes, documenting the test with the kind of precise observations that would be necessary when Schmidt wrote the report that would either convince German military procurement to fund production or convince them that he was wasting time on impractical concepts that violated established principles of aircraft propulsion. The pulse jet was designed for unmanned aircraft. That was the revolutionary application. You didn't need a pilot when the weapon was expendable. You didn't need sophisticated guidance when the target was large and stationary. Just point the aircraft in the right direction, let it fly until fuel ran out, let it crash wherever physics took it. Simple. Cheap. Effective. A flying bomb that cost 200 Reichsmarks to build instead of the thousands required for a conventional bomber, that could be manufactured in days instead of months, that could be operated by anyone who could point an aircraft at a target and press a launch button. German military procurement would either understand this or they wouldn't. Schmidt knew which outcome was more likely. Officers trained in conventional warfare thought in terms of sophisticated weapons and precision targeting and crude aircraft that returned to base after missions. They valued complexity as proof of engineering excellence. They dismissed simplicity as evidence of technical inferiority. A weapon that looked crude and sounded wrong would be rejected regardless of how effective it was, rejected because accepting it meant admitting that their assumptions about weapon sophistication were wrong, and institutional pride prevented that kind of admission. 20 minutes. The fuel gauge showed tank half empty. Schmidt had intended to run the full 47 minutes, but realized that wasn't necessary. 20 minutes of continuous operation proved the concept beyond any reasonable doubt, proved that self-sustaining pulse jet combustion wasn't a fluke or a temporary effect, but a stable phenomenon that could be maintained as long as fuel lasted. Running longer would just consume fuel without adding meaningful data, and fuel cost money that Argus Engine Company was spending from its own budget because no military funding existed for this project yet. He shut down the engine, turned off the fuel supply. The combustion cycle continued for another 3 pulses, residual fuel in the chamber burning through, then stopped. The shutters settled into closed position. The noise ended abruptly, leaving silence that felt unnatural after 20 minutes of overwhelming buzz. The concrete was warm where Schmidt touched it. The engine housing was too hot to touch, radiating heat that made the air shimmer above it. The test stand had stress cracks in the concrete foundation. Nothing structural, nothing dangerous, just evidence that 200 kilograms of thrust generated repeatedly for 20 minutes created forces that building materials weren't designed to endure indefinitely. His name was Paul Schmidt. He was a mechanical engineer specializing in combustion dynamics, which was narrow expertise that most people found boring until suddenly that expertise became relevant to questions about how to kill enemy populations more efficiently. He had spent 3 years developing pulse jet technology, working through hundreds of failed tests that taught him which geometries worked and which didn't, which fuel injection timings created stable combustion, and which created explosions that destroyed test equipment. The engine that had just run for 20 minutes represented condensed experience, failures distilled into working design, problems solved through systematic experimentation. The military procurement office would receive his report tomorrow. 17 pages of technical specifications, test data, performance measurements, potential applications. The data was undeniable. The engine worked. The thrust-to-weight ratio exceeded any competing propulsion technology. The cost was trivial compared to conventional engines. The manufacturing could scale rapidly because no precision components were required. This weapon could change warfare if anyone was willing to listen. But listening required accepting that simple could beat sophisticated, that crude could beat refined, that a buzzing tube that sounded like a motorcycle engine could be more effective than 1,000-horsepower radial engines that impressed everyone who saw them. Schmidt knew which message would be easier for military officers to accept, knew that institutional bias favored impressive complexity over effective simplicity, knew that his report would probably be filed and forgotten unless he found someone with enough authority and enough vision to override the natural conservative impulses of bureaucratic systems. The workshop smelled like burned fuel and hot metal. His assistant was photographing the test stand, documenting the stress cracks and the heat discoloration and the bolt deformation that proved the thrust forces had been real and substantial. These photographs would accompany the report. Visual evidence for officers who didn't trust mathematics, who needed to see damage and deformation, and physical proof that the engine had actually worked rather than just existed on paper as theoretical possibility. Schmidt began writing the report that night. Technical language first, thrust measurements, fuel consumption rates, thermal characteristics, operational parameters. Then applications section, unmanned aircraft, guided missiles, flying bombs. Then cost analysis, 200 Reichsmarks per engine versus 8,000 for conventional alternatives, manufacturing time measured in days versus months, skill requirements minimal versus extensive. The economic argument was overwhelming. The technical argument was solid. The strategic argument was obvious. All of it would probably be ignored because the engine sounded wrong and looked crude and violated expectations about what German engineering excellence was supposed to produce. The report was completed by morning. 17 pages that proved pulse-jet technology was viable, effective, and revolutionary. Schmidt delivered it personally to the procurement office. The clerk who accepted it glanced at the title page, said someone would review it, filed it in the stack with dozens of other proposals from engineers who thought they had invented war-winning technologies. That stack was tall. Most proposals in it would never receive serious evaluation. Most would be rejected through inattention rather than analysis. Most would die not because they were bad, but because bureaucratic systems couldn't evaluate them all and defaulted to rejecting anything unusual. 3 weeks passed. No response. Schmidt called the procurement office, was told his proposal was under review. Called again a week later. Same answer. Called a third time. Was told that pulse jet technology had been evaluated and determined to be unsuitable for military applications. No details provided. No technical criticism offered. Just rejection without explanation. The kind of rejection that meant officials had decided the proposal wasn't worth their time. Schmidt requested a meeting. Was granted 15 minutes with a procurement officer whose name he never learned, and whose technical knowledge became obvious within 30 seconds. The officer said the pulse jet sounded crude. Said German engineering had to demonstrate technical excellence. Said weapons needed to be sophisticated to prove German superiority. Said a buzzing engine that sounded like a toy wouldn't impress anyone, wouldn't demonstrate German technological advancement, wouldn't serve the propaganda purposes that weapons were supposed to serve alongside their tactical functions. These weren't technical objections. These were aesthetic objections. The engine was being rejected not because it didn't work, but because it didn't look impressive. Not because the mathematics were wrong, but because the sound was unpleasant. Not because the concept was flawed, but because it violated expectations about how German weapons should appear and sound and demonstrate the sophistication that proved German engineering was superior to enemy capabilities. Schmidt tried explaining that effectiveness mattered more than aesthetics, that 1,000 cheap weapons were better than 100 expensive ones. That quantity had quality all its own. That wars were won by weapons that worked, not weapons that impressed. The officer listened politely and rejected everything Schmidt said. The meeting ended. The proposal was officially declined. Development of pulse jet technology was forbidden, not through formal decree, but through resource denial and bureaucratic dismissal and the institutional resistance that killed innovation more effectively than any explicit ban. Let's pause here for a moment. If you find value in stories like this, you can support the channel by liking the video and subscribing. After watching, leaving a brief comment, even a simple word, helps more than you might expect. Your support keeps these stories alive and visible. Thank you. Let's move on. The officer's rejection wasn't just bureaucratic indifference. It represented a fundamental misunderstanding of how warfare was evolving, how industrial capacity would determine outcomes more than individual weapon sophistication, how the nation that could produce 10,000 crude weapons would defeat the nation that produced 1,000 sophisticated ones. German military leadership in 1939 was still thinking in terms of quality over quantity, still believing that technical excellence would overcome numerical disadvantages, still operating with assumptions that would be shattered by Soviet mass production and American industrial might. Schmidt understood this in ways that career military officers didn't. He had worked in industrial manufacturing. He knew production timelines. He knew what could be mass-produced with existing tooling and what required specialized facilities that couldn't scale rapidly. A pulse jet was a tube with shutters and a fuel injector. Any metalworking shop could build them. Any factory with basic stamping equipment could produce them in volume. The learning curve was minimal. The quality control requirements were forgiving. A pulse jet that was slightly misaligned or had imperfect welds would still work, would still generate thrust, would still fly and explode when fuel ran out. Compare that to a BMW 801 radial engine, 18 cylinders arranged in 2 rows. Each cylinder needed precise boring to maintain compression ratios. Each piston needed exact tolerances, or friction would cause failures. Each connecting rod needed specific heat treatment, or it would fracture under stress. The crankshaft was a single forging that required specialized machinery to produce and weeks of machining to finish. Assembly required experienced mechanics who understood engine timing and valve adjustment and lubrication systems. Training new workers took months. Quality failures were common even with experienced staff. This complexity meant that radial engine production couldn't scale rapidly. Germany built thousands of BMW 801 engines during the war, but always struggled to meet demand. Bomber losses exceeded production capacity. Fighter squadrons operated with incomplete aircraft inventories. Maintenance consumed engines faster than factories could replace them. The sophisticated technology that demonstrated German engineering excellence was also the bottleneck that prevented Germany from matching Allied production rates. Schmidt's pulse jet had none of these limitations. The combustion chamber was a tube. The shutters were spring-loaded plates. The fuel system was basic injection equipment available from automotive suppliers. The most complex component was the ignition system, and even that was simpler than what was required for a multi-cylinder piston engine. A moderately skilled worker could assemble a pulse jet in 8 hours. Quality control consisted of pressure testing the chamber and verifying that shutters opened and closed correctly. If a unit failed testing, the failure was obvious and could be corrected quickly, or the unit could be scrapped with minimal resource loss. The economic implications were enormous. Germany in 1939 had industrial capacity, but not unlimited industrial capacity. Every resource allocated to one weapon was a resource unavailable for other weapons. Every hour of skilled labor spent on radial engines was an hour not spent on other projects. The pulse jet required minimal skilled labor and minimal specialized resources. It could be produced in parallel with existing weapons programs without significantly impacting those programs. This meant Germany could have deployed thousands of flying bombs while simultaneously maintaining production of conventional aircraft. But the officer who rejected Schmidt's proposal never considered these economic factors. He thought in terms of individual weapon capability, not production scalability. He evaluated the pulse jet as if it were competing directly with conventional bombers rather than supplementing them with a different capability that served different strategic purposes. This categorical error, treating all weapons as if they had to fulfill the same roles and comparing them on the same metrics, prevented recognition that the pulse jet's advantages were precisely its differences from conventional weapons. The strategic opportunity that Germany missed in 1939 was psychological as much as military. Britain at that point hadn't experienced sustained terror bombing. The Blitz wouldn't begin until September 1940. British civilian morale hadn't been tested. British air defense systems weren't prepared for the kind of sustained assault that thousands of flying bombs could deliver. And critically, British leadership hadn't yet committed to the "we'll never surrender" rhetoric that became their defining characteristic after surviving the Blitz. If Germany had deployed V-1s in early 1940, say 5,000 flying bombs launched over 3 months, the psychological impact would have been catastrophic in ways that it wasn't in 1944. The weapons would have arrived without warning. No air raid sirens would have detected them early. No fighter aircraft would have intercepted them successfully. The bombs would have just appeared over London, their buzzing audible for seconds before they crashed and exploded in random locations across the city. This randomness was psychologically worse than targeted bombing. You couldn't predict where they would hit. You couldn't shelter effectively. You could only wait and hope that statistics favored you. This kind of terror might have fractured British political will before it hardened into the stubborn resistance that characterized Britain's war effort. Churchill wasn't Prime Minister until May 1940. The government that existed before him was more willing to consider negotiated settlements. If flying bombs had been destroying London at random for months, if casualties had been mounting without any apparent defense, if the attacks showed no sign of stopping, political pressure for negotiations would have been substantial. Germany might have achieved through terror what it couldn't achieve through conventional military force: removal of Britain from the war, while German forces were still strong enough to turn their full attention to other theaters. But this scenario required deploying the V-1 in early 1940, which required accepting Schmidt's proposal in 1939, which required military officers to overcome their aesthetic objections and recognize that crude effectiveness beat sophisticated ineffectiveness. They couldn't overcome those objections. They rejected the pulse jet. They denied funding. They banned development. And they lost the window of opportunity that might have ended the war before it became the industrial meat grinder that destroyed Germany. The rejection meant Schmidt couldn't get military funding, couldn't access military testing facilities, couldn't recruit engineers with the credentials that would make the project credible to other officials. He was working for Argus Engine Company, which meant he could continue research using company resources, but Argus was a private firm with limited budgets and couldn't sustain expensive development programs that generated no revenue. The PulseJet project was dying through resource starvation, killed not by technical failure, but by institutional indifference. He continued anyway. Built improved prototypes using personal funds and company resources that weren't officially allocated to PulseJet work. Conducted tests that weren't officially authorized. Documented performance that nobody with authority would read. This was the desperation of engineers who knew they had invented something important and couldn't convince anyone with power to care. This was what happened when good ideas encountered bad bureaucracy. 2 years passed. Schmidt refined the design, improved the shutters, optimized the fuel injection timing, increased thrust to 220 kilograms while reducing weight to 28 kilograms, made the engine more reliable, more durable, easier to manufacture. Every improvement made the Pulse jet better. None of the improvements mattered because the weapon was still banned, still rejected, still dismissed as too crude for German military use. The war was going badly. France had fallen quickly, which German leadership interpreted as proof their military doctrine was correct. Their weapons were superior, their strategies were working. But Britain hadn't surrendered. British cities were being bombed, but British industry was functioning. British morale hadn't collapsed. German bombers were suffering losses that couldn't be sustained indefinitely. The Luftwaffe needed new approaches, new weapons, new tactics. But institutional momentum kept them committed to conventional bombing with conventional aircraft using conventional strategies that weren't producing the psychological collapse that German leadership expected. Schmidt's PulseJet could have changed this. A flying bomb that cost 200 Reichsmarks could have been produced in thousands, could have overwhelmed British defenses through sheer numbers, could have created psychological terror that conventional bombing couldn't match because the weapons were uncrewed, autonomous, inevitable. A bomber formation could be intercepted by fighters. A flying bomb just came, unstoppable once launched, crashing wherever its fuel ran out, killing whoever happened to be nearby. This was terror warfare. This was what Germany needed if they wanted to break British morale. but they rejected it because the engine sounded crude. Then everything changed. The strategic situation deteriorated rapidly. Germany invaded the Soviet Union and discovered that quantity had advantages over quality when the enemy could replace losses faster than you could inflict them. America entered the war and brought industrial capacity that dwarfed German production. British bombing campaigns escalated. German cities started burning. The war that was supposed to be quick victory became grinding attrition that Germany couldn't win through conventional approaches. Desperation made officials reconsider technologies they had previously rejected. Someone remembered Schmidt's pulse jet proposal. Someone recognized that cheap, mass-producible weapons might be exactly what Germany needed, now that sophisticated weapons weren't winning the war. Someone authorized a meeting where Schmidt could present updated data and demonstrate that the mocked engine actually worked. This meeting was different from the first. The officers attending were genuinely desperate, genuinely willing to consider unconventional solutions because conventional solutions had failed. Schmidt showed them test data, showed them photographs of destroyed test targets, explained the economics of mass production, explained that pulse jets could be manufactured 40 times cheaper than conventional engines and produced by workers who didn't have years of specialized training. Explained that Germany could build thousands of flying bombs using resources that would only produce dozens of conventional bombers. The officers approved development. 4 years after Schmidt's initial proposal. 4 years of delay caused by pride and aesthetic prejudice and institutional resistance to innovation. 4 years during which Britain had been vulnerable and unprepared, and Germany could have deployed thousands of flying bombs with no effective countermeasures. 4 years wasted because the engine sounded wrong and looked crude and violated expectations about German engineering sophistication. Production began in late 1943. The weapon was designated V1, Vergeltungswaffe 1, Vengeance Weapon 1. The pulse jet engine was manufactured by multiple firms using simple tooling and basic materials. Production scaled rapidly, hundreds per month, then thousands. Each weapon cost approximately 2,000 Reichsmarks, complete with warhead and guidance system, still vastly cheaper than any conventional bomber. Cheap enough that losing them wasn't strategic disaster, the way losing crude aircraft was strategic disaster. The production process validated everything Schmidt had argued about manufacturability. Firms that had never built aircraft engines were producing pulse jets successfully within weeks of receiving technical specifications. The learning curve was minimal. Workers with basic metalworking skills could assemble engines after a few days of training. Quality control was straightforward. Test fire each engine for 60 seconds, verify thrust output, inspect for stress cracks, certify for installation. Units that failed testing were either repaired quickly or scrapped with minimal resource loss. The complete V1 flying bomb was equally simple to manufacture. The fuselage was sheet metal. The wings were plywood. The guidance system was mechanical. A gyroscope for stability, a barometric altimeter for height control, a counter that tracked propeller rotations and calculated distance traveled. When the counter reached a preset value corresponding to distance to target, it cut fuel flow to the engine. The bomb then tipped forward and dove. Simple, reliable, cheap. Everything that conventional aircraft weren't. By mid-1944, production had reached 3,000 V1s per month. This was extraordinary considering that production had started from zero less than a year earlier. Conventional bomber production never scaled that rapidly because bombers required precision components, skilled assembly, extensive testing. The V1 could be mass-produced like automobiles because it was designed for mass production from the beginning. This had been Schmidt's vision in 1939, a weapon that could be built in quantity because quantity mattered more than individual sophistication. But by late 1943, Britain wasn't unprepared anymore. 4 years had given them time to develop defenses. Radar networks had been expanded and improved, with chain-home stations providing early warning of incoming threats. The original radar systems from 1939 weren't designed to track low-altitude, fast-moving targets, but 4 years of refinement had addressed those limitations. By 1944, British radar could detect V-1s at sufficient range to scramble fighters before the weapons reached London. Fighter interception tactics had been developed specifically for flying bombs. Fast fighters like the Hawker Tempest and the Gloucester Meteor, Britain's first operational jet, were assigned to anti-V-1 patrols. These aircraft were fast enough to catch the flying bombs, which cruised at roughly 350 miles per hour. Pilots learned to approach from behind and slightly below, then either shoot the V-1 down with gunfire or use their wingtip to flip it off course, causing it to crash before reaching London. This second technique was dangerous, but became preferred by some pilots because it conserved ammunition and guaranteed the bomb wouldn't explode over populated areas. Anti-aircraft defenses had evolved as well. Guns were positioned in defensive belts around London, concentrated in areas where V-1 flight paths crossed. The weapons flew predictable straight courses at consistent altitudes, which made them easier to target than maneuvering aircraft. Gun crews developed techniques for engaging fast-moving targets using radar-guided fire control systems that calculated lead angles automatically. By late 1944, anti-aircraft guns were destroying roughly half of all V-1s that entered their engagement zones. Barrage balloons were raised to create aerial obstacles. These were tethered balloons flying at altitudes where V-1s typically cruised, with steel cables hanging below them. A V-1 that struck a cable would have its wing torn off or its fuselage damaged, causing it to crash. The balloons weren't individually effective. The odds of any single V-1 hitting a specific cable were low. But thousands of balloons created a hazard zone that V-1s had to traverse, and statistics meant some percentage would be destroyed. These layered defenses meant that roughly half of all launched V-1s were destroyed before reaching their targets. This was much higher than the loss rates for conventional bomber raids, where German defenses typically shot down 5 to 10% of attacking aircraft. But the difference was that V-1 losses didn't cost trained pilots. The weapons were expendable. Germany could lose half of them and still achieve strategic effects as long as production exceeded losses, which it did throughout the V-1 campaign. The psychological impact was significant, but not overwhelming. British civilians who had survived the Blitz in 1940-41 had been hardened by years of bombing. They understood that random death was a possibility they had to accept. The V-1 attacks created fear and stress, but didn't break morale. The British government implemented civil defense measures. Sirens warned of incoming V-1s when the buzzing sound was heard, shelters were designated, evacuation programs moved vulnerable populations out of London. These measures reduced casualties and demonstrated that the government was protecting civilians, which helped maintain morale even under sustained attack. But imagine these same defenses facing V-1 attacks in 1940. The radar network wouldn't have existed. Chain-home was operational, but not yet refined enough to reliably track low-altitude targets. The fighters wouldn't have been fast enough. Spitfires and Hurricanes in 1940 could barely catch a V-1, and pilots hadn't yet developed interception techniques. Anti-aircraft guns weren't equipped with radar guidance. Barrage balloons existed but weren't deployed in the numbers or configurations that became standard by 1944. The defenses that destroyed half of all V-1s in 1944 would have destroyed perhaps 10% in 1940. More importantly, British civilian morale in 1940 hadn't been tested. The Blitz that hardened British resolve hadn't happened yet. Political leadership was still uncertain. Churchill became Prime Minister in May 1940, but his position wasn't secure, and there were still significant political factions that favored negotiating with Germany. If 5,000 V-1s had hit London between January and March 1940, before the Blitz hardened attitudes, before Churchill consolidated power, before British resolve crystallized into stubborn resistance, the psychological impact might have been war-ending. This was the opportunity that German leadership threw away by rejecting Schmidt's pulse jet in 1939. Not just a military opportunity, but a political and psychological opportunity. A chance to break British will before it hardened. A chance to remove Britain from the war while German forces were still strong, while the Soviet Union was still neutral, while America was still uninvolved. A strategic window that closed because officers couldn't accept that a crude-sounding engine might be more valuable than sophisticated technology that impressed everyone but couldn't be produced in sufficient quantities to matter. The first V-1 was launched at London in June 1944. The weapon worked exactly as designed. Flew at low altitude, 350 miles per hour, following a straight course until fuel exhausted and the engine cut out, and the bomb tipped forward and dove into whatever was below it. The explosion killed 6 people, injured 9 others, demonstrated that uncrewed weapons could deliver strategic effects against civilian targets. But it also demonstrated that Germany's 4-year delay had cost them the advantage they should have had. British defenses adapted quickly. Fighters were assigned to intercept flying bombs before they reached London. Anti-aircraft guns were positioned in defensive belts around the city. Barrage balloons were raised to create aerial obstacles. The V-1 was effective, but not overwhelmingly so. Not war-winning, not forcing British surrender through psychological terror the way it might have in 1939 when defenses didn't exist and shock value was maximum. Over the following months, roughly 8,000 V-1s were launched at Britain. About half were shot down before reaching targets. The others killed approximately 6,000 people and injured 18,000. These casualties were significant, but not war-changing. They didn't collapse British morale. They didn't force surrender. They didn't prevent Allied invasion of France. The V-1 was effective, but came too late to matter strategically. Came 4 years after it should have been deployed. Came when Britain was prepared instead of vulnerable. Schmidt watched this from Germany. Watched his weapon finally being used. Watched it kill people the way he had calculated it would kill people. Watched it fail to win the war because it was deployed 4 years too late, after British defenses had been developed, after the strategic situation had become hopeless, after the window of opportunity had closed permanently. The engine that had been banned because it sounded crude was now killing civilians in London, proving that crude effectiveness beat sophisticated ineffectiveness, proving Schmidt's arguments from 4 years ago were correct, proving nothing that mattered anymore, because the war was already lost. Allied intelligence teams captured German documents after the war, interrogated engineers, discovered the history of the V-1 program, learned that Schmidt had proposed pulse jet technology in 1939 and been rejected as too crude, learned that 4 years had passed between initial proposal and operational deployment, learned that the delay was caused not by technical problems, but by aesthetic objections and institutional pride and bureaucratic resistance to weapons that didn't look impressive. The intelligence reports were damning. They noted that Britain in 1939 had no defense against flying bombs, no fighters fast enough to catch them, no radar sophisticated enough to track low-altitude targets, no anti-aircraft techniques for engaging fast-moving autonomous weapons. If Germany had deployed thousands of V-1s in 1939 or 1940, British defenses would have been overwhelmed. Psychological impact would have been catastrophic. Strategic effect would have been enormous. But Germany waited. Waited because the engine sounded wrong. Waited because simplicity looked primitive. Waited until British defenses existed and the weapon that should have been war-winning became merely effective. American engineers examined captured V-1s, were shocked by the engine's simplicity, were impressed by its effectiveness, understood immediately that German leadership had rejected revolutionary technology for stupid reasons. The United States began developing cruise missiles based on V-1 technology. The JB-2 Loon entered production but arrived too late for World War II. But it established the foundation for future cruise missile development. The Tomahawk, modern weapons that traced lineage directly to Schmidt's pulse jet that German generals had mocked as crude. Soviet engineers did the same. Captured V-1s were reverse-engineered. The pulse jet was studied and improved. Soviet leadership understood what German leadership hadn't. That simple didn't mean ineffective. That crude didn't mean bad. That the most effective weapon was the one you could build in quantity and deploy quickly, rather than the sophisticated weapon that impressed engineers but couldn't be manufactured at scale. Schmidt survived the war, was interrogated by American intelligence, told them everything: the early proposals, the rejections, the 4 years of delay, the officers who laughed at his engine because it sounded like a motorcycle, the bureaucrats who banned development because it didn't demonstrate German technical excellence, the pride that valued sophistication over effectiveness, the arrogance that cost Germany a weapon that might have changed the war. The interrogation lasted 3 days. American intelligence officers wanted to understand not just the technical details of the pulse jet, but the institutional failures that had delayed its deployment. They were building case studies about how bureaucratic systems killed innovation, about how to avoid similar failures in American military development programs. Schmidt's story became a cautionary tale used in officer training courses for decades, an example of how aesthetic prejudice and institutional pride could cost wars. The interrogation transcripts revealed details that Schmidt hadn't included in his wartime documentation. He described the mockery more explicitly. How officers had laughed when they heard the engine fire for the first time. How they made jokes about Germany building motorcycle weapons while the enemy built sophisticated bombers. How they dismissed the entire concept without engaging with the mathematics or the test data. The mockery wasn't just unprofessional. It was strategically catastrophic because it prevented serious evaluation of a weapon that could have altered the war's trajectory. He also described the personal cost of the rejection. How he had spent his own money on development when company funding ran out. How he had worked unpaid overtime for years because he believed the weapon was important even when nobody else did. How colleagues had quietly suggested he abandon the project and work on something that might actually get funded. How he had persisted not because he was confident about eventual approval, but because giving up meant accepting that bureaucratic stupidity had won, that good engineering could be killed by bad management, that effectiveness could be defeated by aesthetics. This persistence had psychological costs that Schmidt described carefully in the interrogation. The constant rejection wore him down, made him question whether he was right about the weapon's potential or just stubborn about being proven correct. Made him wonder whether the officers who rejected him saw flaws that he was too close to the project to recognize. Made him doubt his own competence in ways that weren't justified by the technical facts, but were hard to dismiss when every authority figure was telling him he was wrong. But what kept him working was the knowledge that the mathematics were correct. The physics were sound. The test results were undeniable. The pulse jet worked. Officers might not understand it. Bureaucrats might reject it. But physics didn't care about bureaucratic opinions. The engine generated thrust according to equations that were independent of human approval. That objective reality sustained Schmidt through years of rejection, gave him confidence that eventually someone would recognize what he had built, even if current leadership couldn't see it. His interrogation testimony was classified, filed in intelligence archives, not released publicly for decades. It revealed uncomfortable truths about how bureaucratic systems killed innovation, how institutional pride prevented adaptation, how aesthetic preferences trumped strategic necessity. It showed that Germany's technological sophistication had been a weakness rather than strength. That obsession with advanced weapons had blinded them to simple effectiveness. That the most destructive weapon they deployed was one their own generals had mocked as too primitive for modern warfare. The interrogating officer asked Schmidt why he thought German leadership made such poor decisions. Schmidt's answer was simple: pride. National pride. The belief that German engineering had to be sophisticated to prove German superiority. Simple weapons suggested we couldn't build complex ones. Crude engines suggested we were technologically inferior. So they rejected effectiveness in favor of image, rejected weapons that worked in favor of weapons that looked impressive, rejected my pulse jet because it sounded wrong, and in doing so, they threw away potential victory. That testimony captured the tragedy of Germany's V1 program. The weapon worked, the technology was sound, the strategic application was obvious, but it was rejected for 4 years because it violated aesthetic expectations, because it sounded unpleasant, because institutional pride valued sophistication over effectiveness. Those 4 years of delay turned a potential war-winning weapon into a desperate last resort that came too late to matter. The lesson should have been obvious but took thousands of deaths to demonstrate. Wars are won by weapons that work, not weapons that impress. Quantity matters more than individual sophistication when you can overwhelm enemy defenses through numbers. Simple designs that can be mass-produced beat complex designs that consume resources and time. Effectiveness trumps aesthetics. Results matter more than appearances. The mocked solution is sometimes the right solution. The crude engine is sometimes exactly what you need. German generals didn't learn this lesson until too late. They clung to sophisticated weapons and rejected simple alternatives. They valued technical excellence over strategic effectiveness. They let pride prevent adaptation. And they lost the war partly because they couldn't accept that a buzzing, crude-sounding pulse jet was more valuable than sophisticated bombers that impressed everyone who saw them, but couldn't be produced in sufficient quantities to matter strategically. The V1 killed 6,000 people and injured 18,000, terrorized millions, proved that autonomous weapons could deliver strategic effects, proved that simple technology could be devastatingly effective, and proved that arrogance costs more than any weapon ever could. The forbidden engine that was banned for 4 years finally killed civilians in London, but those deaths came 4 years too late to change the war's outcome. 4 years after British defenses had been built. 4 years after Germany's strategic position had become hopeless. They mocked Schmidt's engine, called it a toy, said it sounded like a motorcycle, said sophisticated Germany couldn't use crude weapons, banned its development because German pride demanded impressive technology. And then, when desperation forced them to listen, when pride finally yielded to necessity, they discovered the mocked engine worked perfectly, that crude technology killed effectively, that the banned weapon was exactly what Germany needed. But by then it was too late. Britain had defenses. The war was lost. The opportunity was gone. And the lesson was written across London streets. Arrogance is expensive. Pride is deadly. And sometimes the technology you mock is the technology that could have saved you. The pulse jet engine that German generals laughed at. The crude solution that was forbidden for 4 years. The simple technology that could have won the war but was rejected because it sounded wrong. The weapon that came too late because institutional pride wouldn't let genius succeed until desperation forced reconsideration. That was the V1. The forbidden engine that worked. The banned technology that killed. The mocked solution that proved effectiveness beats sophistication. The lesson that should have been obvious but cost 4 years and thousands of lives to learn. that wars are won by weapons that work, not weapons that impress, and sometimes the crudest solution is the deadliest one. The buzzing sound that terrorized London in 1944 was the sound of institutional failure, the sound of pride costing victory, the sound of 4 years wasted, the sound of an engine that should have been deployed in 1939 finally proving it worked in 1944 when proving it worked no longer mattered strategically. The sound of opportunity lost because German generals couldn't accept that sometimes crude beats sophisticated, simple beats complex, and the mocked technology is exactly what you need.